Welcome back, pre-algebra. We are in lesson 117. After this, we only have 5 more lessons, and then we will be done with the book. Aren't you so proud? I am so proud of y'all. Y'all have come a long way. So let's talk about lesson 117. We're going to talk about equations with x squared. So if I said x squared is equal to 4, we could deduce that x could be either positive 2 times positive 2, which would equal 4, or negative 2 times negative 2, which also equals 4. So we would write that solution set as x is equal to plus or minus 2, because then that gives us a succinct representation of both possibilities. Now, it's important for us to realize that when we plug this into our calculator, let me show you, we're only going to be given the principal square root as our answer. So if I said the square root of 4 in my calculator, I would only be given the positive 2. I have to remember that the negative 2 also applies. So I have to manually apply that here. And remember that it could also be a negative answer. So keep that in mind as we solve the rest of these problems. So let's just jump into the first problem. And in 117.1, we are asked to solve p squared equal to 16. So what we'll do is, the first thing we do is we square both sides. So we take p squared equal to 16, and we square this side, and we square this side, or we unsquare it by using what's called the radical symbol. The radical symbol unfactors, okay? It's like an exponent is telling us how many times to multiply. The radical symbol is asking us for a factoring of two factors, two identical factors. And when there is no number here, the default is 2. If it wants more than 2 identical factors, it will tell us that number of factors here, and that's called the index. So what happens when we ask for 2 identical factors of something that is already squared? They cancel each other out. So we are left with p is equal to the square root of 16. And we know, because we know our multiplication tables, that 4 times 4 is 16. So the 2 identical factors that equal 16 are 4. But we have to remember that it could be positive or negative 4, because positive 4 times positive 4 is the same thing as negative 4 times negative 4. Because a negative times a negative is a positive answer, right? We've already learned that. So let's look at 117.2. We have p squared is equal to 42. So we're going to square or find the radical of both of these. Put the radical sign over both. It cancels here because it's asking for 2 factors and it's giving 2 factors. So p is equal to whatever this is that we can multiply the identical factors. Can we get identical factors out of 42? No, because 6 times 7 is equal to 42. All right? That's as close as we can get to identical factors. They're 1 integer apart. We could also say 2 times 21, but that's not even close. So there are no identical factors here that we can pull out of the radical sign. So what do we put for an answer? In algebra, we leave it in the radical sign. So our answer would be plus or minus the square root of 42. And we leave it just like that. Okay? That is what we do. We do not try to solve it any further. We don't put it in the calculator and try to calculate it. We could do that. We could put it in the calculator and we could say 42, what is the square root of 42? And it would give us some number. Don't do that. That is not the answer that we are looking for. In algebra, we want to see it written like this. I do not want a non-repeating, non-terminating decimal, because then that would be an irrational number. I don't want an irrational number in algebra. I want to have it written as short as possible and as succinctly as possible. I want to just be able to identify this as the square root of 42. That's all I want to do. I just want to see that. All right, so let's move on. And the reason I'm illustrating this is I want to talk to you about the Pythagoreans Theorem. And Pythagorean, he created a formula, or he didn't create it, God created it, but he discovered a formula for right triangles that will always help you find the length of a side in a right triangle if you know the other two. So let's look at that. Let me clear the page. In a right triangle, you have two parts, or three parts. Two of the parts have the same name, which is why I said 3. So here's a right triangle. We know it's a right triangle because this dimension here is 90 degrees. These two sides are perpendicular to each other, which creates a 90-degree angle, which makes this a right angle or a right triangle because we have 3 sides in a closed polygon. So the 3 parts of a right triangle, you have a leg here, you have another leg here, and the part that connects the leg, the side that connects the two legs, is the side that is opposite the right angle. That is called the hypotenuse. My pen is taking forever. There we go. So if you have the side that is across from the 90-degree angle, that is called the hypotenuse, and the other two sides are called legs. In Pythagorean's theorem, he said that if you take the square of one leg and you add it to the square of the other leg, the length is equal to the square of the hypotenuse. He simplified that equation by calling the legs A and B and the hypotenuse C. So A squared plus B squared is equal to C squared. So let me illustrate how that works. If you have, let's just put some measurements here. All right. Let's say that I have, and it's always going to be equal to that. If I have, let's say, let me adjust this a little bit. All right, that looks about right. If this is 3, right, this is 3 inches long, I could actually make it a square here, right? And I'm going to put 3 blocks and 3 blocks, right? So 3 squared would be 9. All right, 3 by 3, that's 9. And this is going to be 4. So I'm going to do 1, 2, 3, 4. Come down. Oh, my pen does not want to stop when I tell it to. So I'm going to make this 4 here. So this would be in half. This would be in half. This would be in half. In half. In half. In half. All right, so I have 3 squared and I have 4 squared. This one is going to be, I don't know if I have enough room to show you. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And it's just a little bit too, where I've positioned it's too long. So this is 5. This is 5 squared. So let me show you how it works. If you have 3 squared plus 4 squared, that should be equal to 5 squared because 5 is the hypotenuse, right? So 3 squared is 9, 4 squared is 16, 5 squared is 25. 9 plus 16 is 25, and that does equal 25. So that checks out. We have found, or not me personally, but mathematicians have found that this has proven true for every right triangle. That, and I'll show you, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. That's this side right here in green. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Would you look at that? 5 by 5 is equal to 4 by 4 plus 3 by 3. And it holds true for every right triangle. So let's do some more right triangles. Let me clear this off. And I'm going to write this formula back at the top so that you have a reference to it. This is Pythagorean's Theorem. It is the Pythagorean Theorem. We always say Pythagorean because his name was Pythagoras. But it is the Pythagorean Theorem. And it is that the area of a square drawn on the hypotenuse of a right triangle equals the sum of the areas of the squares drawn on the other two sides, which is simply a square plus b square equals c square. I'm going to take the equal sign and just put an arrow right there. That is how you solve for the legs and the hypotenuse of a right triangle. So let me give you a right triangle to solve for the legs of. So here is a triangle here, and we have a hypotenuse of 5 and a leg of 4. We don't know what that one is. This is going to be 117.3. We've already done 2 of the problems, and you guys didn't even realize it. How about that? So here's what we would do. We would drop these in where they go. So we have a squared. We don't know what a is. We know b is 4. So plus 4 squared is equal to 5 squared. Does that look familiar? So we have a squared, which we still don't know what that is, plus 16 is equal to 25. So we treat this just like any other formula. We subtract 16 from both sides. This cancels. We have a squared is equal to 9. So then we use our radical symbol and unsquare both of them. This cancels, so we have a is equal to the square root of 9. Now what we would typically do is we would say plus or minus 3. But when we are talking about length, length can never be negative. Length is always a positive. Think about the absolute value. It is a length from an integer to 0 on the number line. It's the same thing here. It's the absolute value of this. So a is going to be equal to positive 3. 3 is the length of that line. All right, so let's do 107.4. And I'm just going to erase this one and use the same triangle so I don't have to draw it again. So 107.4. Here we have a right triangle, and we have a leg of 5 and a leg of 4. And P is our hypotenuse. We don't know what that is. So let's apply Pythagorean's theorem. We're going to say A is 5, A squared plus B squared plus C squared. A is 5, so 5 squared. B is 4, so 4 squared. And you can interchange these. These don't matter because we know with the commutative property, sorry, that should be an equal sign. The commutative property of addition means that we could put them in any order, so therefore we could add these in any order. Either one of these could be A and either one of these could be B. But C squared is going to be P, and we're going to make it P squared. So now we square these. So 25 plus 16 is equal to P squared. So 25 plus 6 is 31 plus 1, that's 41, is equal to P squared. So now we use the radical sign on both of these to unsquare P. So that cancels. So the square root of 41 is going to be, the positive square root of 41 is going to be P, because a length is always positive. But we cannot factor 41, so therefore it has to stay in the radical sign. And typically when we denote the positive, we don't even have to put the positive sign. We can just leave it like this because we always assume that an integer or a number is positive unless it has a negative symbol in front of it. Okay? A number is always positive unless it has a negative sign in front of it. All right, so let us look at one more, and this is 117.5. And I'm just going to change this around a little bit. And I have a leg of 7, I have m as a leg, and I have 9 as the hypotenuse. So let's drop those into our formula. We have 7 squared plus m squared equals 9 squared. Well, 7 squared is 49 plus m squared is equal to 81. So if I subtract 49 from both sides, this cancels, and I find that m squared is equal to, what's 81 minus 49? That's almost 50. So that'd be 32. So 32 is what m squared is equal to. So I unsquare both of these. That cancels. M is equal to, what are the factors of 32? Let's see, we have 4 times 8. We have 2 times 16. I'm not seeing any perfect squares in there, so we would leave this as the square root of 32. And that's it. Even if we factored this out, right? So we could factor this out as the square root of 2. That'd be 2 times 16. Right? 16 is 2 times 8. Then we have, let's see, 2 times 4, which is 2 times 2. So let's see if that's right. That's 4, 8, 16, 32. Yeah. So we could actually take out one set of 2's and another set of 2's. So 2 times 2 times the square root of 2. So we could rewrite this in simplified form as 4 times the square root of 2 is the length of m. That is its most simplified form right there. That's the best we can do. All right. So that is all we have for lesson 117. I will see you in lesson 118. We're getting close. We're almost done.